Lesson 13 is the second lesson of Module 6 and looks at the effect of end conditions on the buckling behavior of steel columns. The effect of end conditions is the last condition we want to look at for imperfect columns. Remember that the Euler column was assumed to have pinned ends. A column can be supported at either end with one of the four different idealized end conditions as summarized in this slide. Both the end rotation and translation of the end must be considered. The third end condition from the top represents an idealized condition where the column is connected to an infinitely rigid beam, but the top of the column can translate laterally when it buckles. Since the end conditions affect the stiffness of the column, and hence its buckling capacity, an adjustment must be made to the Euler formula. We use what is called the effective column length factor, capital K, to account for the change in stiffness due to the different end conditions. The actual length of the column is then multiplied by the effective length factor to arrive at the effective length of the column, L sub C. The Euler column, with its pinned end conditions, is our baseline or reference column. Its effective length factor is therefore 1. By applying the K factor, the length of a column with other end conditions can be adjusted so it behaves like a pinned-ended column. For example, a column with both ends fixed would be much stiffer than a pin-pin column, and hence its buckling load would be higher. Therefore, a K factor less than 1 is used to give it a shorter length, which will result in a higher buckling capacity when calculated using the Euler buckling formula. By mixing and matching the four previously shown end conditions, 6 different columns can be described as shown. The block at the top of the column in 2 cases signifies that the top of the column can translate, but it cannot rotate. Note that both theoretical and design values are given for the different K values. The theoretical value is derived by solving the differential equations for a particular set of end conditions. The design value takes into account that no support is infinitely rigid, as denoted by the fixed support. A concrete foundation supporting a steel column may rotate slightly to the flexibility of the soil. Since this reduces the stiffness of the column, the buckling capacity is reduced. Using a slightly higher K value reduces the buckling capacity. While there is no such thing as a truly frictionless pin, ignoring the increase in stiffness is conservative, and no adjustment is made to the K values for the lack of an idealized pin. Note that 3 of the columns have K values of 1 or less, and the other 3 columns have K values that are greater than 1. We will discuss this further. Shown in table C-A-7.1, which provides the effective length factors in the shown in table CA 7.1, which provides the effective length factors in the AISC steel manual. It is located in the specification commentary on page 16.1-570. This is certainly a page you want to tab so you can find it easily, as it's kind of buried deep in the commentary. Note how the effective length factor, K, is incorporated into the formulas for both the load and stress by using the effective length, L sub C. Note that since the effective length factor modifies the actual length of the column, it is therefore squared along with the actual length. The formula for the Euler elastic critical buckling stress forms the basis of the AISC column design provisions, as we will see in Lesson 14 of Module 7. It is important to note that there are two different types of frames, braced and unbraced. As discussed in Lesson 1, the decision to use a braced or unbraced frame is based on how the lateral loads, such as wind or seismic, are resisted. Brace frames have diagonally bracing, these are tension members, or use shear walls to prevent lateral translation. Unbraced frames have moment connections between the beams and columns to provide lateral resistance. For a brace frame, the top of the column is restrained from translating during buckling. Therefore, the side sway is prevented or prohibited. 3 of the 6 isolated column cases conform to this condition. The effective length factor is 1 or less. For the frame shown, the K value is 0.80 for design and 0.7 for theoretically. For unbraced frames, the top of the column can and will sway laterally when the column buckles. This results in a less stiff situation than a brace frame. For the frame shown, the K value is 1.2 for design and 2.0 theoretically. The 6 isolated column cases just discussed have one of the 4 idealized end conditions. Now consider columns in a building frame. The stiffness of the column ends is somewhat between truly pinned and truly fixed because of the other members framing into the column ends. If we isolate the column, we can simulate the rotational support at each end of the column by springs. The spring stiffnesses are a function of the bending stiffness of each member framing into the joint. Beams or girders that are stiff relative to the column cause the joint to act more like a fixed joint. The bending stiffness at each end of the column is a function of the length and moment of inertia of each member framing into the column. In general, the bending stiffness of the member is given as its moment of inertia times the modulus elasticity divided by the member length. Since the modulus elasticity is the same for all steel members, or 29,000 KSI, the member bending stiffness reduces to the moment of inertia divided by the member length. To get a measure of the moment stiffness, we sum the stiffnesses of the columns framing into the joint and divide through by the sum of the stiffnesses of the beams or girders framing into the joint. This gives us the relative stiffness since it is a ratio. Normally, we need to make sure that our units in our calculations are consistent. In this case only, we can keep the length units in feet since, as a ratio, the units will cancel. You calculate a relative stiffness for each end of the column. Once you determine the relative stiffness at each end of the column, you will use these alignment charts that are shown to determine a K value. To determine the effective length factor, determine the location of the 2 relative stiffnesses on each scale of the alignment chart and draw a straight line between the 2. Where the line intersects the center scale, that is the effective length factor. You can use your student ID card to make the straight line. Note that there are 2 charts, one for brace frames or side sway inhibited, the other for unbraced frames or side sway uninhibited. You can tell the difference between the 2 charts by the K values, which again is in the center scale in both charts. The braced frame chart has K values that are 1 or less, while the unbraced frame chart has values of 1 or greater. Also note that 2 relative stiffness scales are the same for each chart. Therefore, it doesn't matter if G sub A is the top of the column or the bottom. The resulting effective length factor will be the same. The AISC specification commentary provides the alignment charts on pages 6.1-571 and 572. Tab these pages. In the commentary discussion, it is mentioned that if you have an idealized fixed support, use a relative stiffness value of 1.0. If the support is a pin, then use G equal to 10.0. This will happen at the base of the building. The discussion also provides guidance for cases where the other end of the girder or beam is fixed or pinned. The textbook conveniently provides formulas that give approximate solutions for the effective length factors for columns in both braced and unbraced frames, as shown in this slide. While these formulas do require more computational effort than using the alignment charts, they're not prone to the interpolation errors associated with the alignment charts. However, it would probably be quicker to use the alignment charts when performing hand calculations. The K formulas are well suited for spreadsheet analysis, however. Note that it would be nearly impossible to program the alignment charts. These would also be good for MathCAD. Also previously mentioned, the A and B ends of the columns are interchangeable in both these formulas and also the alignment charts. This ends a lesson 13 in Module 6.